In 1956, IBM introduced the 305 RAMAC, the first commercial computer to use a moving head hard disk drive. It weighed over a ton, took up an entire room, and had to be transported via cargo plane. Its total storage capacity was just 5 megabytes, about enough to hold a single modern smartphone photo. Today, you can hold a terabyte flash drive in the palm of your hand. That is 1,000,000 times more storage than the RAMAC, packed into a space millions of times smaller. We often think of digital data as something invisible, a cloud of abstract information. But data is strictly physical. To store a file, you must physically alter a medium. So how exactly do we physically encode trillions of bytes of data into a device the size of your thumb? If you look inside a high-capacity flash drive, you won't find moving magnetic platters. Instead, you find NAND flash memory chips. These chips are packed with microscopic memory cells, and their entire purpose is to trap electrons. A modern memory cell consists of a control gate, a channel, and the critical middle layer called the charge trap, wrapped in a silicon dioxide insulator. When you save a file, the drive applies a positive voltage to the control gate. This attracts negatively charged electrons from the channel. But there is an insulating barrier in the way. To get past it, the drive relies on a principle of quantum mechanics called quantum tunneling. Because the insulator is extraordinarily thin, sometimes just a few dozen atoms across, the electrons don't need to physically push through it. The voltage alters their quantum probability wave, allowing the electrons to simply teleport or tunnel across the barrier and into the charge trap. When the power is turned off, the insulator traps the electrons inside. If a cell contains trapped electrons, it reads as a 0. If it is empty, it reads as 1. That is the physical foundation of all your digital data. But this brings us to a severe physical limit. To fit terabytes into a flash drive, engineers have to shrink these cells to around 20 nanometers wide. If you shrink them any further, the insulating walls become so incredibly thin that electrons start leaking and interference becomes severe, corrupting your data. Since we cannot build wider and we cannot build smaller, engineers did what architects do in crowded cities. They built upwards. This is called 3D NAND. Modern high-capacity drives stack these memory cells vertically, sometimes up to 200 layers high. Furthermore, instead of a cell just holding one bit, a simple empty or full, modern quad-level cells, or QLC, can precisely measure the exact volume of electrons inside the trap. By distinguishing between 16 perfectly calibrated voltage levels, a single microscopic cell can hold 4 bits of data at once. The mathematics of this scale are almost incomprehensible. For example, 12 terabytes equals roughly 96 trillion bits of data. By storing 4 bits per cell, that requires 24 trillion individual memory cells, all stacked, connected, and functioning flawlessly inside this piece of plastic. But this density introduces immense engineering challenges. Because we are manipulating packets of electrons across atomic scales, error is inevitable. Ambient heat, cosmic radiation, or simply reading and writing to the drive too many times degrades the silicon insulator. To prevent the drive from failing, a dedicated controller chip acts as a traffic director. It uses complex error correction algorithms to actively monitor degrading cells, mathematically predicting where data might be lost and quietly moving your files to healthier sectors of the silicon before the electrons can escape. It is a constant microscopic battle against entropy. It is easy to take modern storage for granted. But a terabyte flash drive is not just a digital bucket. It is an intricate, multi-layered skyscraper of quantum engineering. 12 terabytes is enough to hold 3 million high-resolution photographs, or a continuous, uncompressed audio recording playing day and night for over 26 years. All of it is preserved by precisely counting electrons, trapped behind atomic walls, relying on the laws of quantum mechanics to hold your memory safe.